Okay, so we just saw that NAND is alone a functionally complete set of operators. And we can rewrite ANDs and NOTs in terms of NANDs like this. So, and this is enough. Why? Because we already know that not an AND in itself is a complete set of operators. We already know that. So, if we want to write any expression in predicate logic, if we want to rewrite it using only NANDs, all we need to do is first rewrite it using only NOTs and ANDs, and then we eliminate the ANDs and NOTs into NANDs using those two equivalences. So let's apply this strategy to an example to see how it works. Okay, so let's now see an example of how to rewrite an expression in Boolean logic or in predicate logic as using only NANDs. So I'm going to keep the example simple because otherwise it's going to become very cumbersome and long, but I hope the ideas are going to be clear. So suppose we had, say, this expression here. This one uses a conditional, right? And so how can we write this using only NANDs? For a simple expression like this, you could do it by start by writing the truth table, and then from the truth table write something in DNF, and then the DNF is ANDs or and NOTs. We go from there. That's not very practical for longer expressions or with expressions with more variables, because building the truth table could be very cumbersome. But for this one, it's so simple that we can just do it. We will do it in another way later. So let's write the truth table by brute force. And this is just not P biconditional Q. So what is the truth table for the biconditional? It's one only if and only if they are the same. So the negation of this thing is going to be the opposite of that. Right? So we just, okay, this is a truth table for that. How do we represent this in disjunctive normal form? We take the ones and we write one term for each row, take the OR of them. This row here would be represented as not P and Q. And this here would be represented as P and not Q. And we take them together and we have an expression for the whole function. So this is going to be equivalent to not P and Q or P and not Q. And that is completely equivalent. And now we have something that only uses ANDs, ORs, and NOTs. Now, what do we do with that? We are going to eliminate all the operators into NANDs. Now we have an OR here, right? And we don't have here in the table how to eliminate ORs directly. But we do know how to turn ORs into ANDs and NOTs, right? We saw this before. And we could, if we wanted, to write an expression just like those two to eliminate ORs directly into NANDs. Or we could first convert it into ANDs and NOTs, and then convert the ANDs and NOTs into NANDs. So let's take a look at both options. So what I'm saying is, I need to get rid of the OR. What do I do with that? We could just rewrite the OR in terms of ANDs and NOTs, and we already know how to do this using de Morgan's law. So that's one strategy. We could apply this to that, and then we would have an expression that only uses ands and nots, and then we use those to eliminate the ands and nots. So let's proceed with this idea. Let's eliminate this OR using this equivalence here. This equivalence is saying that if I have an OR, I can turn it into this. And be careful here, I'm using the same names of the variables, P and Q here and here, but here, P and Q could be something more complicated than just a single variable, and it has nothing to do with the P and Q here. Be careful about that. So let's make it very explicit. This is an OR of this thing and this thing, right? So if you want to eliminate opportunities or minimize opportunities for confusion, you might even want to write this thing as, say, A or B is equivalent to not A and not B. It means the same, but maybe this helps you not get confused. So this is A, this is B. What does it say? It says that this thing here is going to be equivalent to not A. What is A? Not P and Q. And not B. What is B? P and not Q. Right? So I just used this equivalence here, which is just written into different ways, but means the same, to eliminate the OR from this expression here. And the result was this. So this is equivalent to this, and now this doesn't have an OR. Right? Now, to get something that uses only NANDs, I still need to get rid of the and the nots, right? But now you can take a look at this and see, well, this here is already a not of an and. So this could be very easily be rewritten as a NAND, right? Because this is already a not of an and. So we could rewrite this as an and between this and that. So it would be not P NAND Q. Right? Because this is a not of an and. Of an and of what? This and that. And the not of an and just as a reminder, NAND is exactly that, right? P or A, that's right in terms of A and B. A NAND B is exactly equivalent to not A and B. So that's what I'm doing here. I'm going the other way. Only in this case, this is my A and this is my B. So not this and that is equivalent to this and that. So I did this already. And this is this, so it's this and something else. What? The negation of another and. So I can also write it as an and. So I could write it as P NAND not Q. Right? So this is a not of an and, so NAND. And notice that luckily we already got something that is again a not of an and. So I'm not even using those equivalences in this example because I already know. Well, I'm going to. I'm still going to because of the not. I still need to get rid of the not later. So great. Let's do the next step. Next step here is we realize that this is again a not of an and so we rewrite this as a NAND of the two terms. So that's going to come out as not P NAND Q NAND P NAND not Q, right? Okay, so this here is exactly this part, and this is exactly this part. So it's a NOT of this and that. So it's a NAND of the two. And now all that's missing for us to complete eliminating everything that's not an AND is get rid of those NOTs. How to? And now we're going to actually apply this, which we do by looking at the places where the NOT appears and substituting, right? So here we have this thing here is going to be equal to what? Not P is equal to P NAND P. So we write P NAND P instead of not P. This thing NAND Q. This whole thing NAND what? P NAND not Q. What is not Q? Not Q is Q NAND Q. And you're done. So this expression here, this final one, is exactly equivalent to the original one, but using only NANDs. Right? The whole thing here is using only NANDs. So we managed to, as we always can, eliminate every other operator, and that's what it means to say that NAND is a functionally complete set of operators. It means that we can always do this. We can always start from any expression and end up with something that has only NAND and represents the same function. We could have written a separate rule for OR here, but we didn't. But so let's now do it. Suppose we wanted to write a separate rule for what to do with ORs directly, instead of converting them to ANDs and NOTs, converting them directly to NANDs. So if we have P or Q, we already know that this is equivalent to that. And then we can proceed by looking at this and say, oh, this is already an AND, right? Because it's not of an AND. So we write this thing as not P, NAND, not Q. And then we eliminate the NOTs using that. So that's going to be equivalent to P NAND P NAND Q NAND Q. And notice that this is very similar to the rule for AND. So we could jump straight to NANDs from ANDs, ORs, and NOTs if we wanted.